presentation. My name is Elaine. These are my fellow teammates, Wesley, Oleg, and Sachin. We have constructed a 3D LED cube display for our customer, Professor Breston. This cube displays a 3D image through an 8x8 matrix of 512 monochrome LEDs. Each LED has 64 brightness settings and is USB compliant because we programmed them through a host PC. The entire system is powered through US standard wall socket. Motivations for building such a cube include a 4D signal processing display and perhaps even viewing 3D models. This is a physical picture of our final product, and now Wes will walk us through the operational overview.
Hi. Operating the cube is relatively straightforward. You plug it in, turn it on, connect a PC to it over USB, and then using some tools provided, which I'll talk about later, you can control the image being displayed. The host PC allows you to create images, send the images to the cube, and set the operating mode of the cube. The cube has two operating modes. Static, which allows the user to store up to 100 images on the cube's internal flash. This means that these images are persisted across reboots of the cube. The second mode is stream mode, which allows the user to continuously upload images to the cube to be displayed instantly. Now Oleg will walk you through our block diagram.
Thank you, Wesley. This is a top-level block diagram of our design showing our major components and their interconnections. So the AC high power line goes into our power supply, which provides power to our transistors. These transistors source current to our LEDs, which light up. This current is sunk into our LED driver. Both of these are controlled by our microprocessor, which receives images from the host PC over USB. The only output of our project is the image in the form of light. We're using an 8-bit microcontroller to send control signals to the LED drivers and transistors to turn on 64 LEDs at a time. This group of 64 LEDs is known as a raster group. LED drivers are marvelous little integrated circuits which can precisely control the amount of current that they sink, which will control the brightness of the LEDs that they're powering. They're also capable of storing these brightness values to continually output them. The Darlington configuration transistors are good high-power sources. They are able of sourcing current to groups of 64 LEDs at a time. Our surface mount LEDs were chosen for high viewing angles to create a beautiful picture and relatively high brightness for very reasonable power consumption. In the end, our cube is able to output a 3D image, as you will see. We can upload the 100 images that Wesley mentioned in about 7 seconds. And our program comes with a user-friendly GUI for allowing the user to transfer images to the cube. Additional features include Image Maker, which is another user-friendly GUI to create custom images to send to the cube. And our cube is also capable of animation. The major subsystems of our design are the manufacturing electronics, which include things like making the actual slices stand up, as well as powering the LEDs, making them light up. Also, the software, which is responsible for the control signals to the LED drivers and transistors, which will control the LEDs, as well as our wonderful GUIs to give the user full control. Now Sachin will discuss manufacturing and electronics of our design.
Thank you.
Thank you very much.
So here we see a CAD rendering of our cube. We used polycarbonate to create each of the frames. The housing unit that you see at the bottom here is comprised of a plastic box to which the slices can attach. The wiring we decided to use is 24 gauge bare wiring, and the package we decided to use for the LEDs are the 1206 surface mount LEDs. These last two choices were based on the ability to view the entire cube. So we wanted to use smaller gauges for both small gauge wire, and smaller size components so that we could see the maximum number of LEDs from any angle. Here we see a sample slice from the cube. We have all the power lines and each ground line. So as we mentioned earlier, we turn on 64 LEDs at once, and this corresponds to one column in each slice. So if we turn on the first transistor, it powers the first column of LEDs in slices 1 through 8 by then corresponding the grounds, which correspond, to the LED drivers. By programming them correctly, we can turn on all 64 LEDs at the brightness levels required to produce one raster group. So we repeat this by switching over to transition 2, 3, 4, and so on at a rate fast enough that the human eye sees a full cube. The physical and electrical interfaces are highlighted here. We have a custom support that was designed and manufactured, which allows for easy removal and replacement of slices via these screws. And the electrical connections are custom bent pins that interface with a cable from which we can take, from which we can connect, our PCB. The tools we used for these portions of the project include Autodesk and Inventor and SolidWorks 2008. These were used to create the renderings for the slices and to get the support structure manufactured. For the electrical schematics and PCB, we used Alcyon DXP. To successfully have both units working, the electrical and mechanical, our criteria for that, was to have a mechanically stable set of slices and a housing unit capable to interface with these slices. As you see here, we were successful in both of those designs. We also have a functional PCB. We did notice that there was one minor flaw with the PCB with the USB port. When we connected it to a standard lab power supply, it functions exactly as expected. However, the custom ATX power supply we are using does not work quite as well. The USB does not get detected properly. So we believe that that minor change of switching out the power supply would have a fully functional unit without any glitches whatsoever. Now I'll pass it off to Wes to discuss the software.
Thank you, Sachi. All right, the first tool that we provide our user with is the image maker. With this tool, you are able to open up any existing image, modify it and save it, or create new images. Due to the complexity of modifying 512 LEDs in a 3D space, this GUI allows you to modify one 64 LED slice at a time. You simply select which slice you want to modify. Here we have selected slice 0, and you select the brightness level that you want for that slice. Here we have a little smiley face. We have eyes, a nose, and a mouth. The next GUI that we provide is the display manager. This is the main tool that you use to control the cube. You select the directory of image files that you wish to transfer to the cube, select between the two modes of operation, hit start, and the display manager will transfer all of the images in that directory to the cube. An additional feature this manager provides is the cycle feature, which works under stream mode only. With that checked, the manager will cycle back to the beginning of an animation when the end is detected. A cool little feature with this is that if you select the directory containing one image, select stream and cycle, the display manager will continuously upload that image to the cube, which means if you open up this image in the image maker, any change you make will be immediately displayed on the cube, which is a lot of fun. The USB software has two sides, host PC and microprocessor. On the host PC, we read in images, convert them to 64-byte packets. Each packet contains operation mode, which allows us to easily switch between modes. After sending each packet, we then wait for a handshake. On the microprocessor, we decided to go with the Human Interface Device USB class. While this class is usually used for more interactive devices, we decided to go with it to allow for a speedier USB development. With this class, we are able to receive a 64-byte packet every 4 milliseconds, which gives us a maximum rate of 16,000 bytes a second, which is more than enough to transfer 30 images a second. After receiving a packet, the microprocessor will then send a handshake to the host PC, telling it is ready for the next packet. Now Elaine will talk to you about the firmware.
So in addition to the microprocessor software that handles USB, there are also the programming of LED drivers and the state machine that's in firmware. To achieve 60 Hz refresh rate without any visible flicker, we're using two important mechanisms. The first is to use a real-time channel interrupt to guarantee that the period stays at 2 milliseconds for precise timing of the columns in the raster groups. The second is using a front and back buffer so that whatever is currently being displayed on the cube will always be the front buffer, and the back buffer can be edited and point to whatever is next to be stored. So in terms of the state machine, all it needs to do is update the back buffer. In static mode, it will